Greeting everyone, welcome to this video. So in this video we're going to be covering our VPM graphs. So basically in the exam they usually ask you to draw certain graphs or to interpret certain graph. So the graph that they use or they ask are three graphs, which I have written down here, which is the position versus time graph, the velocity versus time graph, and the acceleration versus time graph. So these are the three graphs that you're gonna come upon on your exams or when you are doing past question papers, right? So you must be able to interpret these graphs, and also you must be able to draw them when you are given a scenario, right? Okay, so we're gonna go through each of these graphs and we're gonna point out the most important things in this graph that you must know for your exam, right? So one thing that you have to note about this three graph, which is a position versus time graph, the velocity versus time graph, and the acceleration versus time graph, is that the shape of these graphs is really determined by the direction that you're going to choose as positive, because remember, this is vertical projectile motion and you are dealing with vectors, so you must always indicate the direction that you're going to choose as positive. I mentioned that in my last video. So your direction is going to affect how your graph sort of is aligned in the Cartesian plane. Okay, but I'm gonna go further with that in the when I'm explaining the graphs, right? So, and the second thing that determines the shape of your graph is also the reference, right? So what I mean about the reference is what I'm also gonna go through this thing of a reference in detail in this video. But basically, when you talk about reference, you're talking about where are you referring to. If I can make an example, right? When I'm saying let's say I take my home as my reference, right? Let's say my home is going to be my zero position. So let's say I'm walking now. I'm gonna walk. Let me make an example. Let's say this is my house, right? This is me, right? And then let's say I'm gonna walk right to this position. Sorry about that. To this position. So say this is position A, this is position B, right? So now, what is the distance that I have covered from A to B, right? Because distance or displacement is relative. In other words, you must say 2 meters from something. For example, if I'm here, I can say I'm 2 meters from my house, right? So my house is my reference. It's something that I'm referring on. I'm saying I'm 2 meters from it. So I use my house as my reference, right? So someone may use, maybe let's say there's a school here. There's a school here, right? And then okay, let's say this is a zero position now, right? So let's say from school, this is school, to my house. This is my house. I will just write house. So let's say this is point C. So let's say if you move from C to A, this is like 3 meters long, but it's really unrealistic, right? But it's 3 meters long. A person at B will say, I'm 5 meters from the school. So this person is using school as his or her reference. So he or she is saying that she is let me just say he is like 3 meters away from school. This one is saying he's 2 meters away from house. So the references are not the same. So your graphs are going to be determined by which reference do you choose. But I'm gonna go deeper on that thing in the later on this video, right? But the basic idea of a reference is what you are referring to like if you are saying I'm 5 meters away, away from what really? The reference help you in that way. You can say I'm 5 meters from something, because if you're gonna walk and say I'm like 5 meters, like 5 meters from what? That does not really make sense, right? So a reference is helpful in that way, right? Because if you say I'm 30 kilometers away from something, that thing is a reference, because you can't say I'm 10 kilometers away from like nothing really. So that is what we talk about when we talk about reference, right? Okay, so but I'm gonna go deeper with that thing in the later on this video, right? So and then um the first graph that you're gonna do is position versus time graph. So I already drawn these two graphs. So the position versus time graph is basically tells us the position of our projectile or of our object at any given moment, right? So let's say I have a ball, right? Let's say I have a ball, and I'm gonna draw this ball up, and then it's gonna go down, 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 right? So this graph really tells us about the position of this ball at any time. So they are like telling us at this particular time our ball is at this height or at this location. So they basically telling us where our object is at a certain time, right? So yeah, so the shape of this graph is usually parabolic, meaning it's like a parabola, right? So it's actually a parabola if you but I will kind of like explain the thing, but you don't really need to know it for the exam, but it's just for interest sake. So it's usually like a parabola like this or like this or like this or like this. These are still parabolas, just that they are cuts, right? But if you can extend like here or here, you will see that these are parabolas, right? So your position versus time graph is a parabola, right? So on our y-axis we have this is y, which means it's just because remember we're talking about a horizontal motion, a motion upon the y-axis. So I'm moving in the y direction. This is our y, right? So this is y, this is y. I can even call it change in y, right? It's still the same thing, right? So this is my position and this is time. So this is a position versus time graph, right? So there are certain things that you have to know about this, but there are not many, right? The one thing that you have to know is that there is a different shape that you can get, but they depend on your scenario, which I'm gonna explain later, right? So this scenario, the second one, you can see that this ball is gonna reach a maximum height, right? Like it's easier to picture this graph because it's like you have a ball which is moving like this, like this, like this, and then it's gonna drop down, right? This shape is similar to this one, which is the same thing really, because this just shows this motion but in a graph, right? So same thing with the first graph. If you can look at this graph, this is a ball which is just thrown like this, right? Thrown like this, and then it's gonna hit the ground, right? So these two things, this one and this one, are the same. It's just that this is a graph, but this is a real life thing, right? So yeah, these are like same thing. You can actually picture them that way. It's like a ball moving up, and then it goes down, and then it hits the ground. But I will explain later about the shapes, like. But what I basically want you to know or to grab from this particular thing that I'm explaining is that is the shape of this graph of position versus time graph, right? And also to know that this is the maximum height, right? So yeah. And then one of the interesting things, you don't have to know this for the exam, but if you look at this graph, this one, you can see this is actually a parabola, right? It's actually like a graph of a parabola because it is actually a parabola, right? And if we look at one of our equations of motion for this one, this equation, right? It delta y is equal to vi delta t plus 1 over 2 acceleration squared. If we rearrange this equation in this way, in such a way that this is in the, we really just swipe the position of this, we can see that this is almost similar to this, right? And this is an equation of a parabola, right? So I can actually rearrange this in such a way that it is the same as this, right? This is the change in y, right? This is y final minus y initial, right? So I can break this one actually as y final minus y initial. And then I can take y initial to the other side. So I can transpose y initial to the other side, right? Okay, let me just clean this one up. Okay, let me remove this. Okay, so now I can move my y initial to the other side. So then I get this, right? You can see that this is y final, this is y initial. So this was just changing y, and then I transpose y initial to the right hand side. And if you can see this is the same as this equation, where this is these two are constant, right? Because a is always constant, it's always 9.8. And then you have t squared, which is the same as x squared. You have vi, which is same as b. T is x, obviously, because even here it was x, right? And then c is y initial. And then if you go to your graph, this is my initial position, and it is actually the y-intercept, because you see that is where it cuts the y-axis. So it makes sense if c correspond with y initial, right? And then you can see from here that that this x correspond with this, because remember on the x-axis we have time. So instead of this x, we can represent the parameter that can take place of x must be time, right, for this to be true. So we can see that in this equation this corresponds very, very well. And we can see that actually this is a parabola. So this is actually the equation of this graph. But then you don't have to know that. You can actually, it can be helpful maybe if you just forgot something, and or maybe you love math, it can be very, very helpful. But it's the one of the most interesting thing that I've discovered, that this formula is the formula for this one. For example, if you want to find the maximum height, from metric, that you just you know how to find a turning point of a parabola, right? So you can go to this graph actually and just try to find that thing. You can do that, but then you don't really have to do that. You can just keep things simple, use your equations of motion. But then yeah, I just wanted to show you that actually this graph is come from this equation, right? So that is one of the things that you have to know, right? And then you're gonna move on to the second type of graph that you have to know, right? Which is the velocity versus time graph, right? So it's this graph actually tells us the velocity of our object at any time. Remember, the position versus time tells us the position of our object at any time. It basically tells us where our object is at any time, right? Maybe after 2 seconds, it can tell us, okay, our object is like at this location, right? But the velocity versus time graph tells us what is the velocity of that object at any time, right? Because remember, when we're drawing an object up or drawing an object down, its velocity is going to change. Remember, I said in the last video, there will be a change in velocity and then there will be an acceleration, right? So there will be a change in velocity. So we can actually find the velocity of an object at any time, right, using equation of motion, right? those equations that I explained in the last video. We can actually use them to find where the velocity of our object at any time, right? Because we have this formula, right? V final is equal to V initial plus acceleration time delta t. So if we know the time a, we already know a, and we know our initial position, we can find where our object is at that time, right? So yeah, so basically the velocity versus time graph basically tells us what is our velocity at a certain time, right? So the velocity versus time graph is a straight line, right? And it makes sense why it is a straight line, but I'm gonna explain that again, right? But it's always a straight line, like it's always a straight line, not a curved line, it's always a straight line, right? So the basic shapes of this are like this shape, right? Or this shape, right? But it will depend. Sorry about that, but it will depend, right? One of the things that you have to know about this graph are like three things, right? You have to know that this is actually the maximum height, this one, where the graph cuts the x-axis. Why do I say this is the maximum height? Because remember, at the maximum height, the velocity of our object is 0. And if you can see here, our velocity at this point where our graph cuts the x-axis is actually 0, right? So that's why this is our maximum height. And same thing for this graph, this is also our maximum height, right? So that is the first thing that you have to know, but you can really just read it from the graph, which is something that you have to practice to read the graph, which is basically very, very easy. I'm just gonna explain it on the last section, on the last part of this video. So the other thing that you have to know, the second thing, is that what does this area, this one that I shaded with purple, represent, right? Because it represents a very, very important thing, but I'm just going to explain it in such a way that it makes sense. Okay, so we know that, let's take one triangle, right? Let's say we take this triangle, this one, right? And then we want to find the area under this triangle. We know the area for triangle is just 1/2 breadth times height, right? And then in this case, our breadth is equal to, it's just the velocity, and then our height, oh sorry, our breadth is actually the time, and then our height is the velocity, right? So we can just represent it like this. So we get this, our area is just 1/2 t times, this is actually v, this is v, sorry about that. And then we can recognize that from this equation of velocity, that velocity is equal to the change in position, or the change in x over the change in time. And then if we rearrange this equation, we get the change in x is equal to the velocity times delta t, which actually correspond with this area, right? Apart from that, there's a half, but then it's the same thing, right? So this basically means that the area under the velocity versus time graph represent the displacement of our object in that section. For example, from this time to this one, if I find the area of this one, it's going to represent the displacement of my object from this position to this position, right? So the area under the graph of velocity versus time represent displacement, right? So in this case, if we have two triangles which are equal, basically this is a scenario where we have a ball which you're gonna draw, and then you're gonna catch it at the same height, right? So that this is at the same height, right? So this is my displacement going up, or this is my displacement going up, which is this, and then this is my displacement going down, which is this. and you can see that these two displacements are the same, right? So it makes sense why these two triangles are the same. But if these triangles was gonna actually become bigger, this means that its displacement is now bigger, meaning that this ball may just well have gone down like this. It actually didn't end where it started, right? Because now our displacement is greater, right? So we will see this graph continuing like this, which indicates this area is greater than this area, meaning this displacement is greater than that displacement. Because if you can see here, let me just draw this thing clear so that you can understand it. Okay, let me draw that scenario again. So I have a ball which is gonna go up, and then it's gonna go down, right? And then let's say you have this. Okay, so this is my displacement, right? Because it makes sense why this represent this portion, because this is the maximum height. So we're going from this to here, which is from this position, initial position, to the maximum height. From the initial position, sorry about that, initial position to the maximum height. So this is our displacement, delta y, right? Sorry about that. So this is basically our delta y, and then from here to here, this is also our delta y. You can see that the displacement of these two things are the same, but obviously they are not in the same direction, because remember, displacement is a vector, right? So it has magnitude and direction, right? But if you can see, the magnitudes of these two displacements are the same, meaning that this area is the same as this area, right? So the question may come and say, what does the sum of these two areas represent? You can say it just represents the total displacement of this ball, because remember, it makes sense. This portion represents this displacement, and then this portion obviously represent this displacement of this displacement. So it represents the total displacement of these two objects, right? But one thing that you have to note is that I think I rephrased that question wrong, right? So because if I'm saying that the sum of these represent the total displacement, remember that the displacement only considers the initial and final position. So when I'm talking about the sum of these, I'm not actually talking about the whole pad. I'm talking about this pad, right? From the initial position to the final position. So that is my displacement, right? Not the total, but because that is going to be the distance. And it makes sense, right? Because you can see that this one is gonna be negative, right? And then this is gonna be positive, and if you add them, you're gonna get something which is really small. It's like you are taking this large displacement, which is this, and you are subtracting with the small displacement. So you're taking this large displacement, you are subtracting it with the small displacement, and then you are gonna get your displacement from the initial position to the final position, right? But if these are the same, like you are saying this minus this, which is just gonna be 0, right? Is it going to be 0? Not really. It's not gonna be 0, because remember, I have to consider direction, but I'm gonna go further with that in my upcoming videos, right? But the basic idea that you have to catch here is that the area under this graph represents the displacement, right? This represents the displacement from where I started to the maximum height, and then from the maximum height to where my ball ended, right? So same thing with this one, but then you can see that it's flipped. It has a negative gradient, right? Basically, you can say these two are the same. It's just that it depends on where or in which direction you chose as positive, right? Because let's say you have a ball. Again, let me make an example. it's gonna go up, the same scenario again, and then it's gonna end here, right? So this is vi, this is vf, right? So if I'm gonna choose my position, my direction as upwards as positive, then my initial velocity is gonna be on my positive x-axis, right? Because my initial velocity is in the same direction as the positive direction, so it's gonna be positive. But if I chose downwards as positive, now my initial velocity is negative, so it's gonna start on my negative y-axis. I mean, this is the y-axis, right? So these are the same graph, it's just that it depends on which direction you chose as positive, right? So that's what I meant about when I said shape is determined by a reference and which direction you chose as positive, right? These are basically the graph, these two graphs represent the same thing, but it's just that it depends on which position you chose as positive or negative, right? So yeah. And then the final thing that you have to know about the velocity versus time graph is the gradient, right? Because you can see this is a straight line, meaning that it has a constant gradient. So the gradient is the same, right? The steepness is the same at any point, right? So now the question is that what does the gradient of this graph represent, right? So we have to remember what gradients mean. Remember that from math we know that m, which is the gradient, is equal to the change in y over the change in x, right? So in this case, what is on our y-axis? It's v. So the change in v, what is on our x-axis? It's t. So the change in v over the change in t. So, and then we can notice now that this expression is kind of similar to this expression for acceleration. And it's actually the same, meaning that our gradient for the velocity versus time graph represent the acceleration, right? So the gradient of the velocity versus time graph basically represent the acceleration of that object. But remember, the gradient of this line, because it's a straight line, it is constant, it does not change, meaning that it have a certain value which is constant. And then we have to recall that as our object is moving, we said that it's going to undergo a constant acceleration of 9.8 meters per second, meaning that our gradient is going to be this value, which is 9.8 meters per second, right? It's always constant, right? So our gradient is always like this for the velocity versus time graph. It represents the acceleration, which is 9.8 meters per second. Don't forget to say downwards. You always have to indicate direction. Always, once you have velocity and acceleration, always note your direction, right? So we know that the equation for a straight line is y is equal to mx plus c, and then we can just substitute our values and find the equation of this line that we have. So it's, remember that our y-intercept in this case is the initial velocity, right? And this is our initial velocity. So our y-intercept is the initial velocity, and then our gradient is 9.8, right? And on our x-axis we have t. So instead of this x, we can represent this with t, and then y in this case is gonna be v final, because it's what we are looking for, right? What is the velocity of an object at a certain time? That is our final velocity, right? So we can see that this equation represents that line, and actually this equation comes from this equation of motion, right? You can see these two are the same, because you can even just replace this with 9.8 meters per second, you will get the same thing, right? Sorry about that. So yeah, that is what you basically have to know about velocity versus time graph. You have to know how to grow them. You have to know the area under the graph. You have to know the gradient. Yeah, and then what else you have to know about, you also have to know you have to be able to interpret this graph, right? Which is the most important thing, which is something that you usually ask a lot in the exams. And then the last graph that we're gonna do is acceleration versus time graph, right? So acceleration versus time graph is a very easy and short graph to understand. You don't have to know a lot of things. You just have to know a few things, right? So it's just gonna be a straight line like this, a horizontal straight line, because it's always the same. It's any time as our body is moving on the air, our acceleration is just 9.8. So it's any moment in time, our body is going to experience an acceleration of 9.8 meters per second, which is why, sorry about this, meters per second squared. I mean meters per second squared. So our body is going to experience a acceleration of 9.8 meters per second squared at any time. So it makes sense why our graph is just a horizontal straight line, because at any time is the same as 9.8 meters per second. But the most important thing that you have to know about this and also for this graph, you have to also consider your direction, right? If you chose upwards as positive, then your acceleration is gonna be negative because it's downward, right? So this line is actually gonna be on the negative y-axis, right? So you also have to notice your direction before you draw your graph, which direction you chose as positive, right? Because if you're just gonna draw this graph and you chose your direction as upwards, you chose your direction as upward as positive, then this is wrong, because your acceleration is not positive, because you chose upwards as positive, and our acceleration, remember, is going down, right? So it's negative. So if you put a positive acceleration, then you're wrong. You have to draw it like this. Sorry about that. You have to draw it in the negative y-axis, right? So you have to draw it in the negative y-axis, right? So yeah, that is one of the important things that you have to note for both velocity versus time graph and acceleration versus time graph, right? So, and then this is the most crucial thing that you have to know about this graph, right? You have to know what this area under this graph represents, because the gradient is something that we can't really explain. It's not part of the curriculum, right? So the area, remember, this is a triangle. So if we want to find the area of a triangle, we know that we have to just say its length times the breadth. So what is our length is just the change in t, so it's delta t. And then what is the breadth or the height? It's a, so it's acceleration. So this is our area. And then again, we have to notice that this we go to this expression for acceleration, and then we manipulate our acceleration so that we make v the subject of the formula, and we can see that this expression is the same as this expression. So this basically means that the area under the acceleration versus time graph represent the change in velocity. Remember, it's not velocity, it's the change in velocity. It's v final minus v initial, right? So the area under the graph of acceleration versus time represent the change in velocity, right? You must always remember that, right? And then that is basically what you need to know about acceleration versus time graph. You have to know about the area and the graph that it represents the change in velocity, right? So, and then for the last part of this video, I'm gonna go through I'm gonna explain this part of reference, right? So this thing of reference is very, very important, especially in position versus time graph, right, is very, very crucial, because they're gonna ask you, they say, draw a position versus graph of this object, take the ground as zero, as the zero position, take the top of the building as a zero position. You have to know what they mean when they say that, right? So this is what I'm going to be explaining in this part of the video. So what they basically means when they say that take the ground as a zero position, or take the top of the building as a zero position, or take the top of the building as your reference position, they are basically telling you where your graph should start, right? So where your graph should start and where it should go, right? Like the shape of your graph. When they say take the ground as the zero position, they mean that since this is our zero position, so that means that this thing is the ground, right? So if you have a building and then you have an object which is just thrown downwards, and then they say draw the position versus time graph of this thing and take the ground as a zero position. So your graph is actually going to start from the ground, right? So it's going to start from here, from the ground, right? So in this case, it's actually more of something like this. It's more of something like this in this case, right? Is it? No, it's not. Sorry about that. I think I made a mistake. So for the case that I drew, I mean, it's more of something like this, right? So this is my ground. This is the ground. So I basically place this thing here. So this is my object. It's gonna go down, then hit the ground. So the same thing here, but for this particular scenario, it's like you are drawing a ball up like this, right? So this is where your ball gonna start, and then this is your ground. So that is where you're gonna hit the ground here. So that's what they basically telling you when they say take the ground as your reference position, or take the ground as a zero position. So they're basically telling you where your graph, how your graph should look like, right? So when they say take the top of the building as a zero position, you do the same thing. You put the top of the building in your zero position, which is the y-axis. So this is my zero position, this is my building. So yeah, for this case, when they say take the top of the building as a zero position, you can see that now our graph is gonna look more like this, right? Because this is our building, and our object is gonna start from the top of the building, then it's gonna go down, right? So yeah, but for this case, if you can draw your graph, you will see that this is the top of the building actually. So it's actually gonna start like this, right? For this particular case, it's gonna start from the top. This is the building, top of the building, then you're gonna draw it up, reach the maximum height, then goes down. So that's what this thing basically telling you, where your graph to start and how it should look like. But then we're gonna do questions based on this, so you're gonna actually grasp this concept, right? So that is what they basically telling you when they say to take the ground as your zero position, take the top of the building as your zero position. This is what they are basically explaining to you, the shape of the graph and where the graph should start. So that is it for this video. I hope you understood. And then don't forget to subscribe, and then I'm gonna see you on the next video, where I'm going to be making an example on how to actually draw this graph from an when you are given a question and then you are asked to draw this graph, and then I'm gonna do that for you in order for you to kind of grasp this graph of vertical projectile motion and then after that I'm gonna do a practice question so that you can understand these graphs and also understand the topic as well. Thank you for watching. See you on the next video.